Hi all, and welcome to this episode of Climate 201 from Physical Attraction. This episode, we're going to be talking about energy efficiency in buildings. In the last episode of this mini-series on energy efficiency, we talked about the efficiency cornucopian view, the idea that a great deal of our effort to fight climate change and general environmental degradation can simply arise from using energy more efficiently than we do today. We talked about Amory Lovins and the Rocky Mountain Institute, as well as Reinventing Fire, the book that presents a plan for maximum energy efficiency in the future of America. We discussed in the last episode specifically how this relates to transport, and we pointed out some of the potentially vast emission savings from increased efficiency in transport, as well as all of the different reasons why it hasn't actually been adopted in reality. This is all part of a broader analysis and critique of the efficiency cornucopians, making the argument for energy efficiency's importance, but also pointing out why the view that maximises its effects from Lovins and so on may be a little bit too rosy. And I want to move on to another sector which is analysed here, which is buildings. Buildings account for a substantial fraction of the energy use in society and hence emissions of any economy. In the US, those figures are approximately 42% of the US's primary energy consumption, 72% of its electricity, and 34% of its natural gas in 2010. If buildings in the US were an independent nation, they would use more energy than all countries but China and the US. And this is true for many, many nations as well, that buildings are a huge drain of energy and a huge consumption source of energy and hence a huge source of CO2 emissions. Now it's worth noting that the energy use of buildings in the US has never trended downwards. Buildings have always tended to use up more energy as time goes on, as greater electrical appliances, more industrial storage, heating and cooling and so on is applied. Depending on your point of view, this implies that there are obvious savings to make from using that energy more efficiently, or it might contradict the efficiency utopian thesis simply because history shows that people aren't focusing on using less energy in buildings, and instead on having bigger and better buildings with more things inside them. But the point is made, according to the Rocky Mountain Institute's analysis, that efficiency savings in buildings cost you around 3 cents per kilowatt hour, compared to the retail price of electricity at 9 cents per kilowatt hour. In other words, financially speaking, it would be far cheaper to save a kilowatt hour of electricity through upfront efficiency investments than to actually pay for it on the open market if you're not being efficient. So, in a world where everyone is rationally self-interested maximisers of their own future expected wealth value, or whatever mainstream economists want us to be, you might expect that people would actually make those investments and thereby slash their electricity bills. So what type of recommendations are really being made here to improve the energy efficiency of buildings? Well, one obvious thing you can do is to make the appliances within the building more efficient. And this covers pretty much everything electrical. LEDs are often talked about. Projections from the US Department of Energy suggested they would save by 2030 nearly as much electricity as was used for lighting in 2010, and efficiency is continuing to improve relentlessly as costs reduce. Aside from things like technological developments like LEDs, which consume far less energy than incandescent bulbs, many are other standard things that you're probably expecting when we talk about efficiency in buildings. Insulation, double glazing, designing buildings with a certain layout that has energy efficiency in mind. There is a specific issue with the urban heat island effect. The dense concrete jungles of cities that many of us live in trap heat, in part because they're darker and drier than the surrounding land often is, and so they end up being warmer than the surrounding area. This in turn increases demand for air conditioning and refrigeration, which are two big consumers of energy and result in the release of a lot of greenhouse gases. So some ways to get around this, at least in urban areas, might be light-coloured roofs, paving and planting vegetation which can reduce the urban heat island effect. There are also some emerging technologies worth considering that might improve the energy efficiency of buildings. Some of these include, for example, smart windows. These would darken in response to heat or electric currents, and they can vary their level of opacity with the amount of heat energy incoming depending on outdoor temperature. The advocates, including one of the serial CEOs who have developed these companies in the past, suggest that if this was applied everywhere, it could reduce heating and cooling bills by up to 30%. Another example is enhanced evaporative cooling for air conditioners. So this is effectively spraying small amounts of water all around the place, and these water things basically take in energy as the latent heat of evaporation. This is less efficient in climates that are already humid, obviously, but you can get around that with a desiccant substance that dries the air before injecting the mist. And these These enhanced evaporative coolers have shown a lot of promise theoretically, but they've actually struggled to be adopted in a widespread way since 2010. There are things like insulation with aerogels and nanogels rather than traditional fibre materials that we use at the moment, and these can have better gaps in them effectively that insulate heat more effectively and can do so about 6 times better than plastic foam according to their manufacturers. Another example of an insulation technology that people have thought about for a while that could be better for energy efficiency is so-called phase change materials. So the idea here is that you have an insulator that effectively insulates by absorbing heat in melting. So you could use wax capsules, for example. And this is not really that dissimilar to an evaporation cooler. They rely on the same principles, which is basically that if you look at most substances, it requires a lot more energy to change them in phase from solid to liquid or from liquid to gas than it does to actually heat or cool them by 1 degree Celsius, for example. And when substances are going through these phase transitions, essentially what happens is that they stay at the same temperature while they're absorbing or emitting heat. So you could imagine a case where you fill your walls with this kind of material, and then you have something that during the day when it's hot absorbs heat and melts, and then at night resolidifies and emits that heat again. So it's sort of regulating the temperature of the building simply by putting this big thermal inertia block which has to be pushed either side by hot or cold temperatures. And these things would repeatedly melt and solidify. So you don't need any requirement for an external source of energy, but you have a source of insulation that cools you down during the day and heats you up at night. The key then is to pick a material that has a change of phase at around the desired temperature, say exactly at room temperature of 20 degrees or so. That way you've got a big thermal mass that wants to stick around at 20 degrees Celsius at all times. This has been floated for a while as an idea, and it does seem to make a lot of sense. But so far, the few products that have tentatively come to market, like National Gypsum's thermal core, have been quietly dropped. For now at least, bulk insulation tends to be cheaper, and so we're not actually using these technologies in the way that we could. Now these innovations and these types of technology are part of a move to what's been called passive house. So a passive house is this idea of a house and building that basically just stays at the correct temperature without any active heating or cooling at all. Depending on how the passive house standard is defined, these buildings, through their clever integrated design, typically use 75 to 95% less energy per square foot than the average building. Such buildings are being constructed today, but they're usually one-off projects so far, with around 20,000 such buildings certified around the world in 2010. So let's talk about how you actually achieve this, how you get heating and cooling without any external heating or cooling sources. You might start with a south-facing house that would be heated by the sun in the northern hemisphere. The colour of the exterior of the house can be chosen for heating or cooling purposes. You might have something like triple glazing with noble glasses between the glass panes for further insulation, so-called super insulation in the walls, which substantially reduces heat exchange with the outside of the building. For this reason, these buildings are extremely airtight, with only this passive ventilation allowed, which again reduces the amount of heat exchange you get with the outside. And this point is really critical, because the more heat exchange you have with the outside, the more difficult it's going to be for you to actually heat or cool your building, because you're going to continually have hot air flowing in from outside or cold air flowing in from outside, and it's going to counteract the effect of what you're doing artificially. So you want to make sure that you can, as far as possible, prevent there being these heat exchanges from the outside. Obviously, to do this, you do have to necessitate that you are taking some extra safety measures to ensure that the air remains clean inside the building, but typically passive houses have been able to do this. In some passive houses, the insulation and so on that they have is so good that they can actually rely on a substantial fraction of their heating coming from waste heat from electrical appliances and people living in the house, which is no longer a waste product when your room is gradually heated up by your light bulb or your oven or whatever. That's actually the thing that is now heating your house. Typically, when you've got to that level of efficiency, you can actually dispense with a central heating or cooling system altogether, and instead just have a small heat pump for the coldest days. Passive houses are of course typically more expensive to construct, but the extra costs across various projects in Europe and the US are only reported at around 5 to 10% of the total cost of the project, depending on the project. So typically, if your passive house works really well and you don't need much of a heating or cooling system at all, you would expect the savings in your heating and cooling bills to pay for that after a few years. One good point that Lovins does make in his book is that we need to consider 2 types of energy use and hence emissions that are associated with buildings. The first is the operating energy use. That's the use of energy in actually running the building, all of the appliances aside it, and so on. and the second is the embodied energy use, the use of energy in constructing the building initially. Typically, the operating energy use ends up being much larger than the embodied energy use for most of these buildings. And this is useful because it means that even if you have to build extra components for passive houses using fossil fuel energy, you'll still save on emissions in the long run. This, by the way, is a common canard that, for example, electrifying transport or building renewable power generation has to deal with from its critics, including recently Michael Moore in that infamous documentary he put out. They will say that the huge levels of action you need to undertake will result in their own energy consumption and emissions. Now, it's true that in a carbon-intense society, you can't make or do practically anything without emitting CO2 at some point along the line. But people have indeed thought of this, and the full life cycle impacts of doing these things are constantly being assessed in the academic literature. And it's frankly misleading to state that doing these things would somehow lead to more emissions in the long run. In other words, we know that we've got a lot of activity at the moment that's driven by energy use from fossil fuels and CO2 emissions. If that activity is preventing you from emitting further CO2 in the future, that's the only kind of activity that actually has a net positive impact on CO2 emissions. So of course, it makes more sense to do this than to stick with what we're doing. When it comes to the embodied energy in buildings, though, there are some solutions that you can consider too. Trends like the increasing popularity of mass timber as a carbon-neutral fuel and as a means of carbon storage have some momentum behind them. However, as with anything biological, such as biofuels and so on, you do have to be careful with the full life cycle assessments of the material to be sure that it actually is green, and other non-climate environmental impacts are also important. So of course, a good part of the problem here is going to be in considering the inertia that exists in the stock of buildings that is there at the moment. Even if every new building is constructed to a passive house standard, which is still quite a radical policy step in a lot of countries, it's not something that is happening in Europe yet, then you're still going to have a significant stock of buildings that will continue to be carbon intensive. And this is a big problem with this thing we talked about, lock-in and inertia when it comes to high carbon systems. New build properties today are expected to last for at least 60 years. If we look at the UK as an example, 38% of the houses that are on sale at the moment, or that are being lived in at the moment, were built prior to World War II. So the overwhelming majority of them that exist today were constructed before the 1980s, so they're at least 80 years old. So essentially, if you're building something today, then you can expect it to still be in use probably for another 50, 60 years at least. When we consider that the aim here is to actually get to net zero emissions in wealthy nations by 2050 to have a reasonable chance at the Paris Agreement, it's clear that a lot of retrofitting of old buildings is going to be needed. We can't just rely on constructing every new building to carbon neutral standards, which we're not even doing. So again, this is a classic example of where the basic facts of the situation, the inertia that we're dealing with, and the timescale that we have left to act on, even for action that some people would consider not to be that ambitious, dictates that we start doing something pretty urgently. I've discussed in previous episodes how I think there would be obvious multiple benefits for a massive programme of retrofitting homes for energy efficiency. It would create jobs, save everyone money on their energy bills, and reduce emissions. Again, if we take Lovins's figures for granted, the typical return on investment for these energy efficiency measures is as much as $4 for every $1 that's spent. So the only people that aren't really going to benefit from this are the fossil fuel companies. Lovins in Reinventing Fire points to the impressive retrofit that was done on the Empire State Building as an example of what can be achieved. Apparently, when this was done, it saved 38% of the company's energy use, and it paid for itself within the first 3 years. And he would again argue that the typical energy efficiency savings that might be available in buildings are far cheaper than paying for that energy yourself. Perhaps 2/3 cheaper when you're saving electricity, and half as cheap when you're saving heating energy from natural gas. But of course, I did promise to come at this from both the optimistic and pessimistic point of view, and there are reasons that this massive programme of energy efficiency retrofits hasn't happened yet. I mean, we're portraying it as such a win-win situation for everyone, so why isn't it taking place? Among these problems, of course, are the same old inertia story that I talked about before. Again, leaning on the US as an example, there are 120 million buildings with millions of different owners. To retrofit them all, to fit things to them that would make them more energy efficient, would require each of those people taking some kind of positive action. Getting funding, whether it's from the government or from somewhere else, hiring people, overseeing the project, and so on. And in a lot of ways, each of these projects has to be done in a fairly bespoke manner. It's not as if there's just some simple magical energy efficiency device that you can install in each house without even considering the layout of the building or anything like that, that will work and be the optimal solution for your dwelling. Each building will have its own history, its own area where it loses energy, its own possible solution, from heat pumps to electric heaters to combined heat and power, for example. And of course, they will all be subject to their own set of local regulations and procedure for carrying out whatever works are necessary to do. And we don't live in a world where the market is completely fluid. There will be people that you'll have to find and hire, and if no one in your area knows how to do these things, then it won't be possible for you to get someone to do them. Another huge barrier is the fact that, especially as house prices continue to get unaffordable, renting is on the rise. In the UK, 38% of homes are rented in one form or another, and the fraction that's private rentals out of that is also on the rise. And this raises the thorny issue of who pays for the upgrade. The tenants are unlikely to pay for it on properties they'll never own. The landlords won't pay for it if the tenants are stuck paying the bills for inefficient properties and the bills are not included in the rent. So it's hard to see what can be done other than regulation and incentives here that is going to say to people, if you're renting a house, it has to come up to a certain standard of energy efficiency, because otherwise you're really going to struggle. Another barrier that has certainly been a pretty big issue historically is that at least one of the major players, the gas and electricity companies, have not that much incentive for you to become more efficient. If you're inefficient, they can actually sell you more energy. Having the utility companies on side would be a big deal, because they are the people who actually have access to all that data about how customers use energy, they have billing relationships with their customers, they have the infrastructure to have a presence in people's homes, and they have access to a lot of financing. Typically, the fact that they might actually be happy if you're wasting the energy they sell you has been a big perverse incentive. But there are some examples of individual utilities deciding that it's actually cheaper to have people to use their existing capacity more efficiently than it is to have to build new capacity to supply increasing demand. So in other words, they actually want their customers to use energy more efficiently so that they don't have to build a brand new power plant but can serve a bigger city or a more popular city or more buildings with higher energy demand with less. There are also plenty of cases where regulators will reward utility companies for cutting customer bills or beating energy efficiency targets. So again, there are examples here where sometimes the market incentive works with you and sometimes governmental and regulatory incentives can work with you, but it's not necessarily obvious that this major player of the gas and electricity companies are going to be all in for energy efficiency all the time. So when we're looking at the energy efficiency in buildings then, it's worth looking at the actual trends here. And Lovins does a nice kind of Kaya decomposition if we want to get into the weeds here. You'll remember briefly that the Kaya decomposition is this idea of trying to work out what the drivers are of global CO2 emissions. So we're talking about the GDP per capita, how wealthy the world is, how the world is producing its GDP, whether it's producing it with CO2 emissions or not, how clean our energy use is, and the population of the world. And it's this idea of, okay, let's look at each individual factor that's driving these things. Is it because of population growth? Is it because of economic growth? Is it because we're using more energy? Or is it because the energy that we're using is dirtier, basically? And so you can do similar decompositions to try and work out what's driving energy use in buildings in the US. So the actual energy use per square foot in buildings in the US has fallen by around 30% from 1980 to 2014. The only problem is that in that time, floor space has increased by about 80%, which more than offsets these improvements, and floor space has continued to grow pretty rapidly over time. Much like global CO2 emissions, the energy use of buildings has never trended downwards. Even as we have got more efficient in the way that we use energy, and the way that we use energy in buildings, the constant demand for more and more floor space, more and more buildings and so on, has just meant that the total consumption has gone up. Reversing this, or even achieving efficiency gains that offset the extra floor space that's being used, is going to be a pretty monumental effort. And I think there is a further barrier that doesn't get mentioned enough, which is really a barrier of sexiness. If you've made it this far, and thank you very much, you've listened to probably 20 minutes of pretty in-depth discussion about how to make buildings more energy efficient. How often have you listened to anything like that? How often have I listened to anything like that? When I'm reading this out, I feel like I'm a double glazing salesman or something, telling people, oh, you'll save money if you install that double glazing. Compare this to the endless discussions of new technologies that will save us from climate change, and you start to see the fact that energy efficiency isn't cool or widely discussed, that it doesn't really fit into our narratives to learn to be thrifty, to talk about retrofits, and to think about energy consumption on the demand side. And this has been a big problem. There's a book out recently, which I'm hoping to read soon, which basically makes this point. They call it the innovation delusion. And the point is that because we're so focused on innovation and because we're so focused on brand new ways to solve problems, because that's the only way in which we think of solving problems, we actually miss out on the fact that there's so much cost out there that it actually just comes down to maintaining the systems that we have already. It's not about building something that's brand new, but actually making sure that the things we have work in many cases. And I think that's been true of energy efficiency for a long time. I think a lot of these technologies have been known about and have been accessible to us, but we've not been willing to direct the funding and the efforts there because we're waiting for some brand new technology to come along that will save us. And it's not necessarily the case. The problem here is that sexiness does actually influence decision makers. If you're not thinking about it or discussing it as someone who owns a property, then you might have no idea about the benefit it could have for the environment or the money that you could save, let alone any schemes or policies that may be available to help you. In fact, this stuff is so relentlessly unsexy that half the time we don't even measure it properly. David Mackay's book, Sustainable Energy Without the Hot Air, points this out pretty well. How much do we even know where the biggest sources of waste are in our own homes? Do we know what's consuming the most electricity? It's not even standard for most people to have in their houses a little app or a little panel that says what's consuming what levels of electricity. It's not metered in that way in many homes, certainly not in mine. Are we aware of the energy efficiency of products when we buy them? Maybe. They have a certificate. Do we look at it? Do we know what's good? How often do any of these things factor into our decision making? If the information isn't even available, let alone something that we talk about, then there's no chance that people are going to make these shifts in a voluntary way. In terms of businesses, for example, Lubbins points out that many of them view the energy costs as some kind of fixed overhead and don't bother to try and optimise them. They just get paid alongside rent by accountants, and there's nothing you can really do if you're renting a building to reduce that rent as a business. And because it's low on people's list of priorities, there are lots of extra barriers beyond the obvious financial one that most people don't have enough money lying around to do something like an efficiency retrofit without significant help. There's the hassle factor of figuring out what to do, how to do it, getting it done in the first place. Now, there are things that are increasingly being talked about, like smart meters that will monitor and allow for a more detailed demand-side control of how appliances and heating systems use energy, perhaps linking them to the cost or carbon emissions to allow these things to be reduced by turning on your devices at a certain time and so on. This is a side of the dream of sticking a chip into everything. Supposedly, you're going to be able to leverage the massive amounts of data you're harvesting to actually optimize performance in some way. And monitoring this stuff would be the first step to fixing it. I saw a good presentation recently by some people from Google where they operate these vast data centers which use a huge amount of electricity to run the servers and keep them from overheating. A monitoring program did allow them to save some pretty substantial emissions from these data centers. And frankly, this is going to be necessary anyway because we're going to have more and more things that are run using electricity, and more of our devices will depend on electricity, more and more heating and cooling will as well. And you'll have a grid with an increasing fraction of intermittent renewables providing power. So you can actually go a long way if you have some demand-side management, some ability for people to change their optional energy use to times when there's more production and lower demand. So it's also going to be a necessary step for us to be able to do this and switch these things on and off to have a more renewable and sustainable grid in the future. In some ways, the first step here might be to be installing these in the buildings and then do a huge campaign of initial surveys of these buildings so that we can identify what the best measures are to take, what it is where we're actually using and losing energy and using it inefficiently, and to make the recommendation for projects which can then be financed in the future. This episode of Physical Attraction is sponsored by Podcorn. Some of you out there may be fellow podcasters, e.g. if you're in our Science Podcasts Facebook group. If so, you'll know the extraordinary amount of work that has to go into researching, writing, recording and editing your own show. If you're a small indie show like this one, getting sponsorships to make what you do even remotely sustainable can be tough. Podcorn are aiming to change that. It's a place where podcasters can go to pitch ad space on their shows to people who might want to work with them. If you're a podcaster and you want to find out more, check out the Podcorn link in our show notes, and thanks for listening to this and helping me buy more caffeine. The problem is that you can really achieve the most substantial savings and the best effect by timing the changes and upgrades to a point when the work was going to be done anyway. Imagine that you own a property and you're going to replace the boiler. You don't know anything about the green alternatives. You just know that your boiler's broken and you want to get a new one. The average life expectancy for a boiler is 10 to 15 years. If you just install a new gas-fired boiler instead of something clean, you're going to make it so much more expensive to switch later on, and you lock in the emissions from heating that house for a decade. If you decide to switch when you're already replacing the existing kit, then any extra upfront costs will be small compared to the savings. But because energy efficiency and these green alternatives are not at the top of people's minds, they're not aware of the benefits, and sadly there are not an awful lot of people installing these things at the moment, then a lot of terrible decisions are being made at all the time, and this is unfortunate. So this is a good place for the policy to come in. In Austin, Texas, for example, they've mandated that when you sell a property, it has to have an energy efficiency check and get a rating. Yes, it's another hoop to jump through if you're selling, but you can then at least find out which buildings are the most efficient. It can be a point of merit for including which building you want to sell and which one you want to buy, and you can improve them if you want to improve the value of the property. The sad thing is that this lack of sexiness thinking is still very pervasive. And in fact, this very thinking is literally said to influence decisions in the halls of power. So here in the UK, for example, the Conservatives had a manifesto pledge to spend billions more on energy-efficient buildings, which is one of their policies that I would applaud as very sensible. But then there were rumours that a government advisor wanted to divert the money into funding for something more future-focused, nuclear fusion instead. Loyal listeners may remember our 25-episode series on nuclear fusion. Maybe I'm part of the problem here, but the conclusion I came to from that is that while fusion may be very sexy and inspiring as a technological project, it may not arrive in time to save us from climate change or reduce emissions substantially at all, if it arrives ever. Yet, if this advisor does achieve his reported aim, then it will be another example where we've literally diverted money from something that we have to do anyway, which is energy efficiency, into some sexy technological project in the hope that that will come along and save us. And that would mean that the tangible gains we can achieve from energy efficiency will lose out yet again. Even though I'd argue that not much could be more future-focused than ensuring that we aren't wasting masses of energy in our buildings for the next few decades. And I'm not saying don't fund nuclear fusion, I'm just saying don't pretend that funding nuclear fusion is some viable alternative to making energy more efficient, because, hey, if you could make the energy demand of this country half as much as it would be by the time you build your nuclear fusion reactor, then you will only need to build half as many nuclear fusion reactors. And those things are expensive to build. The problem here is that every time someone does build something new that doesn't reach this level of efficiency, they're locking in an inefficient system for longer, and they're less likely to retrofit or replace something that's brand new. In some countries, for example in the Middle East, where lots of major construction projects are ongoing, there are cheap prices for subsidised energy from fossil fuels, which mean that there's not much incentive to focus on energy efficiency, and so these buildings will be locking in bad practice for a much longer time. Even in so-called climate-conscious Britain, which is certainly doing well at decarbonising the power sector, we see that these energy efficiency measures and design-type measures are well off track. Back in 2019, the Independent Committee on Climate Change issued a pretty damning report about this. They said, quote, "The technology and knowledge to create high-quality, low-carbon and resilient homes exists, but current policies and standards are failing to drive either the scale or the pace of change needed. Home insulation installations have failed. Key policies like the Zero Carbon Home Scheme have been weakened or withdrawn. Policies to encourage property-level flood protection, water efficiency devices and window shading are weak or non-existent. UK building standards are inadequate, overly complex and not enforced, and local authorities, faced with insufficient resources, are largely failing to address the need for low-emission, climate change-resilient homes." End quote. So that was a pretty damning report on a country that's supposedly doing quite well on climate change. Since I'm already dipping toes into politics here, which is inevitable when you want to talk about this kind of thing, I think it's worth saying that a lot of this does come down to a mindset that's overly focused on growth at all costs, rather than whether we're actually spending our money and finite planetary resources wisely to achieve things that are most beneficial to people's lives. Just like in the Kaya decomposition for economies as a whole, it's going to be very difficult to reduce the energy footprint of buildings if we insist on building endlessly more square feet of buildings at a rate that offsets any efficiency changes. And the growth mindset also explains why people would rather build another 50 power plants than use energy more efficiently. Without wanting to sound too much like your grandparents now, it explains why people would rather buy a new thing and throw the old one away than repair or reuse or recycle an old one. And of course, this is not only a problem on the end of the consumer, but also on the end of the producers of these goods, We have this issue whereby, for example, one of the things that could be done if you wanted to reduce the embodied energy in a building would be to make sure that you need to buy things less often, right? I mean, everything takes energy to produce, construct, transport all of the materials that assemble it and so on to an individual place. If you were to mandate that you extended the warranties of things so that your fridge freezer would last for 20 years or 30 years rather than 10 years, so that your TV would last for 5 years or 10 years more than it would at the moment, and so that there wasn't this constant drive to replace things with the newest model, then we would have a far more energy efficient society. The problem is it would also be a less profitable one for the manufacturers of these things. That's why there's a new iPhone out every 18 months, which everyone is expected to buy. It's got nothing to do with the development of technology and the must-have killer applications that the new one can do that the old one can't. It's the fact that these companies have successfully convinced people that this is a status symbol that they need, and therefore is getting them to throw away their phones every 18 months, every 2 years or whatever, when a more realistic and more sustainable and more energy efficiency way to behave would be to have devices that last for 5 or 10 years rather than 1 or 2. It explains why, though, this growth mindset really explains why, rather than investing your money in projects like retrofits, which will save and make money in the long run, alongside all of their environmental benefits, most people with capital lying around would rather invest money in the stock market, achieving faster returns with more liquidity than investing in sensible efficiency measures, which will realise profits at a slower rate. Because when your focus is maximising GDP as rapidly as possible, and that's the main thing you're interested in, you are going to engage in practices that are inherently wasteful. GDP doesn't care whether you waste energy or not. All it sees is the aggregate production, and not whether the results of that production actually go towards anything that you would consider useful. In fact, the more wastefully you live, as long as it's somehow sustainable for you to do so, the more you will contribute to GDP, as long as you can sustain that wasteful lifestyle. And as long as we have a system and a mentality that doesn't only never emphasise how bad it is to waste things, but actually often glamorises and incentivises people to engage in wasteful practices, we are going to struggle to make the changes that are needed. That's not a hippie thing to say, it's just obvious. And it's simply the case that for far, far too long the system has incentivised people to invest in financialised instruments and financial engineering rather than actual practical engineering. According to Statista, total energy efficiency spending in the US has been around $40 billion a year over the last few years, across all businesses, across all of government. Those who have listened to our series on SoftBank will realise that this is basically on the order of what one company spent on pursuing a lot of tech startups with bad business models. $300 billion is being held in cryptocurrencies at the moment, which are essentially, by and large, instruments of financial speculation at this point. So again, you can see how this $40 billion a year is not actually that much when you consider that it's how efficiently we use all of energy. And it's well short of the levels of investment that Lovins himself foresaw to unlock the savings that he's talking about in his book, Reinventing Fire. The issue, then, is that you have this capital being diverted into asset bubbles and financial speculation, rather than practical engineering projects that employ people and improve fundamental conditions on the ground. Like, for example, whether or not a business is profitable in the long run, regardless of how its bets on the financial markets go. I'm reminded of the fact that billions of people in the world may be undernourished or malnourished today, depending on the standards you set for it. But we do actually produce enough food to feed 10 billion already, if we only distribute it properly and didn't waste nearly as much as we do. But the growth mindset wrongly views this as a production problem. People keep thinking, well, we just need to make sure that everyone has enough, we need to make more food, we need to figure out how we're going to grow twice as much food as we do today. And we're viewing this as a production problem when it's really one of distribution. And I think in the climate and energy space we can certainly be guilty of a similar fallacy, where we focus on how much energy we need to produce to satisfy the needs of 8 or 9 billion people consuming as much energy as present-day Americans do, rather than how much energy we actually need to consume to satisfy our needs, and what those needs really are. So specifically, to fix the problem of energy efficiency in buildings, what would we need? Well, Lovins does make some good suggestions here. He says the first thing to do is to monitor energy use and make sure people know about the ways they can reduce it. Give them access to ways to do so at the point where decisions are being made about buying new equipment, refurbishing, whatever it may be. People need to have that information there so that they can make the green choice. We need to regulate to get the energy utility companies on board with the programme. We need to provide a lot of easy-to-access finance for retrofits and the upfront costs for projects. Given that energy efficiency projects are quite low risk to carry out, it's the kind of thing that you could easily turn into a bond where the savings on the energy bills turn profits onto that loan. So for example, you could imagine a case where you would get from the government lots of money that you can only spend on energy efficiency improvements. And then, for example, they might freeze your bills for the next 5 years, and the difference that you would get from your bills would go back to them to repaying the loan or paying interest on the loan. And, eventually that would pay for itself, and then everything after that would belong to you, and you would benefit from living in a more energy efficient house. You could train and educate a workforce with efficiency in mind who can find these energy savings opportunities and design and install the appropriate solutions. Again, this is a huge issue, and this is part of the inertia that we're talking about here. If you decide that what everyone needs is super duper fancy quadruple glazing, then that super duper fancy quadruple glazing industry is going to have to scale up in time to fit every single building that needs it in time for whenever your CO2 emission goal is, if you want that level of energy efficiency to be part of it. And another major thing is to change the mentality in how buildings are being designed and built to concentrate on energy efficiency so that future buildings are all being made to these high standards like the Passive House standard. And this should be something that, every architect, everyone who's interested in this field, and I know there'll be people listening who are much, much more interested in this and know much more than I do, as there always are. But this is something that everyone who's involved in that should have at the forefront of their mind when they're coming up with these designs. Now in this episode, we've really only just scratched the surface of what we could be talking about here. I'm not an energy efficiency expert or an architect, as I've said, but thankfully there are plenty of people out there who are doing some great work in this space, both academically and on the ground. I hope that I persuaded you that to discuss climate change, it's worth spending a lot of time talking about energy efficiency in buildings. Because the thing with climate change that I don't think is appreciated all that much is that it's not about replacing a few coal-fired power plants. In transport, in agriculture, in buildings, in the infrastructure that exists around us, there's a large amount of deeply rooted and deeply embedded inefficiency, and that can mean carbon emissions when your energy source comes from CO2. In this sense, it's a difficult problem because the sheer levels of inertia we have to push against to make the changes happen are quite high. Fixing these problems is going to require a lot of effort on behalf of a lot of different players throughout society. It's not just a case of some magical technological bullet that will solve the problem. Tech developments will of course help in all of these individual fields, and they are being made. But actually translating our words and desires to live on a more sustainable planet into practical actions is the next step. And there are things that we can do in the institutions and organisations that we belong to, where we can have an influence. We all live in and use buildings all the time. We can ask, are they efficient? Is there a plan to make them more efficient? If not, why not? And we can be persuasive. Yes, it may not be the sexiest topic in the world. But when we take these actions, we will do so knowing that we're saving money, saving energy, and saving the planet. What could be hotter than that? Now, we're not done with energy efficiency. In the next few episodes, I want to talk about energy efficiency changes in the industrial and electricity sectors, and I want to talk about concerns surrounding the rebound effect, the so-called Jevons paradox, and we'll get onto that. And then I want to sum up the pros and cons of what we've learned, preferably in as efficient a manner as I can manage. You've been listening to Climate 201 from Physical Attraction. You can find us on the web at physicspodcast.com. There you will find the contact form. You can get in touch with us. That goes to my email. I've loved getting your emails lately. I've had some brilliant emails from all of you guys. So many interesting questions and comments, particularly on some of the different topics that we've done that are outside of physics, and I really appreciate that discussion. And we'll do listener mailbag episodes in the future, so if you have a question that you think would be good for the whole class to learn about, then you can ask me that there, and I'll try and respond to you all in person if I can. You can follow us on Twitter at PhysicsPod. We're on Facebook, Physical Attraction. If you like what we do, you can support the show financially. We have a PayPal link, which you'll find on the website at physicspodcast.com. And we have a Patreon, patreon.com/physicalattraction. There you'll get access to some bonus episodes that only patrons have, and you'll get access to as many early episodes as I've produced at that time. As I'm recording this now, there's 15 that you will get access to straight away. I don't know what that will be by the time this comes out, but hopefully a similarly beneficial number. And of course, it's all about the principle of supporting the independent creators who are making the stuff that you like, with no support from massive conglomerations or anything like that. There is, of course, one other important way you can support the show, which is to tell other people who might be interested in it, who might be interested in these topics, who might be interested in listening to the show, to listen to it. And by that way, we expand our audience. You can review us on platforms of note to see if we can get more attention that way, all that kind of thing. And talk about us on social media. You know all the stuff that you can do, I'm sure. But the most important thing you can do out of all of that is until next time, please do take care.